Okay, so let's continue our discussion of independence. Now, a special case of independent random variables is when all the random variables are identically distributed. Now, this is actually the basis of statistics. What do you do in statistics? Well, you either do repeatable experiments where each experiment is the same, and you try to estimate a quantity from those repeated experiments, or you take a sample from a population where each individual is drawn independently and randomly. In both of those cases, what you really have are n experiments where the results of each experiment don't interact or relate to the results of any other experiment, and you're actually repeating the experiment n times. So in both of those statistical experiments, you're dealing with independent, identically distributed random variables. So you can't underestimate the importance of this concept to statistics. Okay, so the only thing that you're adding is they're both independent and they have the same CDF, which means if they're continuous, they have the same PDF, and if they're discrete, they have the same PMF. Okay, and we'll be seeing plenty of examples of this later on. All right, now, often when you take these independent, identically distributed random variables, you take the sum. Well, here let's consider the sum of arbitrary random variables and consider the statistical quantities associated with that sum. We can take the expectation and we can take the variance. Okay? And we have two formulas. We have the formula for expectation. You sum the expectations. For variance, it's a more complicated expression. You have the variance plus 2 times the covariance. Notice that here you're just summing over I less than j. So these x's are always different. Now, I could also do this if I wanted to. I could just take off the 2 and make that I unequal to j. It's the same thing. Just if you do I less than j, it's more or less computation. But you can see that because if you just do I less than j, you're only taking the terms when this index is smaller than this index. But for every one of those terms, there's a term where the indices are switched, so that's where you get the 2 from. All right, well, it's useful to give a proof of this in the case where the random variables are, I'll just do the case where the random variables are continuous. So let me go back here and just put this here. And let's do the proof. Now remember, in this case, let me go back here because we have the hypothesis that y is the sum of random variables. Put that here. And let's see how we can prove this. It's really not that complex. Let's take the EY is going to be the integral. And this is because y depends on x1 through xn, we have to integrate over the PDF of x1 through xn, which I write as vector x. This is a function of x1 through xn, where these are little x's. And then here you have x1 up to xn. I'm sorry, you're adding the expectations. So I can write this as x1 plus xn, like that. dx, x, again, I do the variables backwards. It doesn't really matter what order you put these in. And I'll put this as integral of from minus infinity to infinity, minus infinity to infinity. Okay, so if I want e of y, I have to put y in here, and I can just break this sum up because this x1 doesn't depend on anything else, I can just pull it out. Times x1 dn dxn dx1 plus, and then all the integrals are going to be like that. Now, what is this? We can rewrite this as the integral from minus infinity to infinity. I'm just going to do this one term. All the other terms are similar. It's going to be the integral from minus infinity to dx1, and I'll have an x1, and then what integral am I going to have inside? This is all the other integrals over all the other variables. Sorry, somehow I got slanted here. And here's fx, x1, xn, and then this should be dx2, dxn. Let's make that bigger. It's really too small, and maybe I can get rid of the slant. If I want to redo this integral and write it better, I'm going to write integral from minus infinity to infinity, and that's dx1. And I have an x1 here, and then in here I'm integrating another integral, which is integral from minus infinity to infinity, and this is going to be fx, x1, xn, dx2, dxn. Now this we've seen before. This is actually equal to fx1 of x1. And let me see if I can convince you of that. Go back here and let's go up. That was the marginal distribution. Right here. Okay, so that is the distribution for x1. So when I have this sum, I can break it up into sums of marginal distributions. That means that this expression here is simply equal to ex1. And then you're going to have the other terms are going to be the same. So I wrote the whole sum out here. Here I just wrote the first term, and I'll just place plus similar. And this is plus similar. And then this is plus similar. Okay, so that's how the expectation works. Now we also have an expression for the variance. And let me get there, right here. Okay, so this is a little more complicated. Let me show you how to do that. Remember what variance is. The variance of y. The easiest formula to use is the expectation of y squared minus the expectation of y squared. All right, so we can write this as the expectation of, now remember what y is. Y is the summation of x1 through xn. So I can say k equals 1 to n of xk. And I'm going to write it like this. I'm going to write k equals 1 to n. I really want to square that, but I'm just going to write it as a sum over another index. Okay. So these are two identical factors, which is the same as the square. Now this is similar, but you need to be careful. This is the expectation of y is the expectation of the sum. And here I can just, let's use another index, L equals 1 to n of xl squared. All right, so how am I going to deal with this? Look at this first one. I can combine these sums into a double sum. It's the expectation of the sum k equals 1 to n, sum j equals 1 to n, xk, xj, okay, minus, I can do similar here. remember that the expectation of a sum is a sum of expectations. Okay, so I can write this as the sum L equals 1 to n. That's what we just proved up there. The expectation of a sum is a sum of expectations. So I can take the sum outside like this. All right, now, here's also an expectation of a sum. I can take the sums outside. Sum k equals 1 to n, sum j equals 1 to n, xk, xj. Okay, and then here I have minus what? Well, let me write this again as a sum of as a product of two identical sums. I'm running out of indices. I guess I can use m. Okay. And now I can write this also as a double sum. So I actually have a double sum on the first group of terms and the same double sum on the second group of terms. So instead of using L and M, I'm going to switch back to K and J. So I can write this as sum K equals 1 to N, sum J equals 1 to N. And here I have xk, xj. Whoops, I forgot the expectation. Sorry, put that in there. Put that in here. Okay. And then minus, what do I have? Well, I can make the L into a K and the M into a J. So I just have expectation of xk, expectation of xj. Okay. So my double sum, let's move it back a little bit so we know see what's going on. Okay. My sum involves this difference. Now, what do you have here? When k equals j, that's the same as the variance. Okay. When k is unequal to j, that goes to the covariance of xk, xj. Okay? So you have these two types of terms. If you see how these group together, the k equals j terms are going to give me this part here, and this part here. And the k unequal to j terms are going to give me this part here. So that's how I get my formula. Right? So we'll stop there.